Every breath you take contains atoms forged in a star's violent death. The universe transforms its greatest endings into spectacular beginnings, creating the very elements that build planets and life. By the end of this journey, you will understand the precise cosmic events that crafted the iron in your blood and the calcium in your bones. We will uncover how a star's final cataclysm can seed the galaxy with gold and reveal the moment a dying star briefly outshines its entire home galaxy. What part of your own existence feels most connected to the cosmos? Our sun's steady light is a testament to this long period of stability. For billions of years, it has performed a perfect balancing act, the outward push of energy from its core precisely countering the immense inward crush of gravity. This main sequence phase is the star's adulthood, a predictable and enduring chapter. Yet this stability is built on a foundation of constant, furious transformation. Deep within its core, the star is a relentless factory, fusing over 600 million tons of hydrogen into helium every single second. This process is the star's engine, and the fuel it burns so efficiently is what makes its eventual death not just an ending, but a necessary prelude to creation. The entire future of the star and the elements it will one day scatter across the cosmos is written in its very first moments. A star's initial mass is its destiny. A star born with much more mass than our sun lives a far hotter, brighter, and tragically shorter life, racing through its hydrogen fuel in a cosmic blaze of glory. Conversely, a smaller, lighter star will burn its fuel with frugal care, shining for trillions of years. It is this initial mass that determines the star's final act, setting the stage for the violent and beautiful processes that forge the elements of life itself. This initial mass is the single most important factor in a star's cosmic legacy. A star like our own sun, considered a lightweight in the stellar world, will meet its end with a kind of quiet dignity. After billions of years, it will gently puff its outer layers into space, creating a beautiful but fleeting planetary nebula. All that remains is a dense, Earth-sized ember called a white dwarf, which will slowly cool over eons. But the story is utterly different for the true giants of the cosmos, stars born with many times the mass of our sun. These colossal furnaces live fast and die young, and their immense gravity is the key to their creative power. This crushing weight forces the star's core to become unimaginably hot and dense, allowing it to perform feats of alchemy a star like our sun could never achieve. It begins fusing the helium left over from its hydrogen-burning phase into carbon. Then, it uses that carbon as fuel to create neon. The neon fuses into oxygen, the oxygen into silicon. It is a desperate, layered process, building elements like a cosmic onion, with each new shell of fusion fighting to hold back the star's own immense gravity. This relentless forging continues until the core produces iron, and with the creation of iron, the star's fate is sealed. Every other element forged in the star's core released energy when it was created, energy that pushed outward and supported the star against its own weight. But iron is different. Fusing iron does not release energy, it consumes it. The star's engine has suddenly, catastrophically, run out of fuel. In an instant, the outward pressure that has sustained the star for millions of years vanishes. And with nothing left to hold it up, the star's core begins to collapse under its own immense weight. What happens next is one of the most violent and transformative events in the entire universe. Iron marks the final, unbreakable limit for a star's creative heart. While forging every element up to this point has released life-giving energy, fusing iron atoms together does the exact opposite. It drains energy, acting like a sudden brake on the star's entire power plant. In an instant, the core's mighty engine sputters and fails. The delicate balance that held the star up for millions of years is shattered. With no outward push from fusion left to fight it, the star's own immense gravity becomes an unstoppable executioner. The core, now laden with this useless iron, has nothing left to support its colossal weight. It simply gives way. What follows is one of the fastest and most violent collapses in all of nature. In less time than it takes to blink, a core that was once larger than our entire planet is crushed down to a sphere only a few dozen miles wide. The matter there is squeezed to an almost impossible density, greater than that of a single atomic nucleus. A single teaspoon of this material would weigh billions of tons on Earth. This is the Iron Catastrophe, the star's point of no return. Yet this ultimate collapse is not the end. It is the trigger for the star's most spectacular act of creation, a final, defiant rebound that will rip the star apart and seed the cosmos with the very elements that make our world and us possible. That inward collapse is so violent it creates an equally powerful outward rebound. The outer layers of the star, plummeting inward at an unimaginable fraction of light speed, do not simply vanish into the new neutron core. They slam into its surface a boundary of unimaginable hardness. The energy of this impact has nowhere to go but out. In a literal bounce of cosmic proportions, the infalling material is hurled back outward as a titanic shockwave. This is not a gentle ripple, it is a planet vaporizing front of energy, supercharged by a ghostly flood of neutrinos pouring from the collapsing core. Together, the shockwave and the neutrino blast tear the star apart from the inside out. This is the detonation of a core collapse supernova. For a few glorious weeks, this single dying star can emit more light than every other star in its home galaxy combined. It becomes a temporary beacon, a cosmic forge of almost unimaginable power. Within that expanding fireball of stellar debris, temperatures and pressures reach levels that only exist in such an apocalyptic event. It is here, in the heart of this cataclysm, that the star completes its final creative act, forging a legacy of heavy elements that will one day form new worlds. This final, furious blast creates a storm of subatomic particles. Trillions upon trillions of neutrons are set loose, flooding the expanding cloud of stellar debris. Within this chaotic environment, a special kind of alchemy begins. It is called the Rapid Neutron Capture Process, or the Are process for short. Picture an atomic nucleus trying to build a wall in the middle of a blizzard. The neutrons are the snow, falling so thick and fast that the nucleus can't help but be buried. It captures one neutron, then another, and another, all before it has a chance to shed any of the extra weight through radioactive decay. This rapid, relentless bombardment forces the nucleus to swell into a heavy, unstable, and temporary form. It is an isotope that could never exist under normal conditions. Then, almost as quickly as it was formed, this overstuffed nucleus begins to settle. It undergoes radioactive decay, transforming its unstable identity into something permanent and stable. This is the cosmic origin of the heaviest elements in the universe. The gold in a wedding ring, the platinum in a catalytic converter, the uranium that can power a city. All of these were born from this frantic neutron blizzard inside a supernova. For a few fleeting moments, a dying star becomes the universe's most prolific jeweler, forging precious metals in a fire that outshines galaxies. This scattering is the star's ultimate gift to the cosmos. Within that supernova fireball, a process called nucleosynthesis reaches its climax, a final burst of creation that forges the last of the star's elemental legacy. The intense heat, far greater than the star's core ever achieved during its life, and the flood of neutrons create a chaotic workshop where atomic nuclei are smashed together and rebuilt. Elements like silicon and sulfur, painstakingly layered during the star's final years, are now ripped from their orderly shells and thrown into the mix. Here, in the fury of the blast, they can fuse into even heavier atoms. This is how much of the calcium that strengthens your bones and the iron that carries oxygen in your blood was cast into the universe. The explosion acts as a cosmic shotgun, blasting this newly forged material outward at millions of kilometers per hour. This enriched cloud of gas and dust, now pregnant with the elements for rocky planets and living organisms, begins its long journey through the interstellar void. It seeds vast regions of space with the raw ingredients for future solar systems. Every world that forms from this material carries the chemical signature of that long-dead star. So the iron in the ground beneath your feet and the calcium in your skeleton were once part of a cataclysm that briefly outshone a galaxy. This is the profound cycle of cosmic death and rebirth, where the end of one star is the very beginning of countless new possibilities. That expanding cloud of stellar debris becomes a new cosmic structure, a supernova remnant. For thousands of years, this colossal cloud of gas and dust, now rich with newly forged elements, continues to expand into the void. It is not a quiet expansion. The remnant plows through the surrounding interstellar medium, the thin gas that fills the space between stars at speeds of thousands of kilometers per second. This collision creates immense shock waves like a cosmic sonic boom that heat the gas to millions of degrees, causing it to glow in X-rays and radio waves. We see this in objects like the beautiful and intricate Crab Nebula, the tangled, luminous aftermath of a star seen to explode on Earth in the year 1054. But these remnants are far more than just celestial gravestones. They are active, dynamic recycling centers. The very same shock waves that light up the gas also compress it. They can slam into nearby, quiescent clouds of molecular hydrogen, squeezing them violently. This compression can be the final push that overcomes a cloud's internal support, triggering its gravitational collapse. Inside these newly collapsing clouds, pockets of gas begin to coalesce, growing denser and hotter, until nuclear fusion ignites within them. A new generation of stars is born. The iron, oxygen, and silicon forged in the supernova, along with the gold and uranium created in its final moments, are now woven into the fabric of these infant solar systems. The death of one star, therefore, directly sows the seeds for the birth of many others. This is the universe's great cycle of renewal, where an ending in one corner of the galaxy guarantees a new beginning in another. But the collapse of a giant star is not the only way to forge the elements of our world. There exists another, equally spectacular type of stellar death that operates on a completely different principle. This is the story of the type Ia Supernova, a thermonuclear bomb triggered not by gravity's collapse but by a stellar theft. It begins with a white dwarf, the dense, cooling core of a star like our Sun, which has ended its life peacefully. Yet if this white dwarf has a companion star in a binary dance, its quiet retirement can be violently interrupted. The white dwarf's immense gravity can slowly siphon hydrogen and helium from its neighbor. This stolen material accumulates on its surface, building up layer by layer, increasing the pressure and temperature at its heart. The white dwarf is essentially putting on weight, and this act of cosmic gluttony pushes it toward a razor's edge. There is a precise and unyielding limit, known as the Chandrasekhar limit, of about 1.4 times the mass of our Sun. Cross this line and the star's fate is sealed. The intense pressure becomes too much to bear, igniting the carbon fusion that had been dormant within the white dwarf. But this is not the controlled burning of a normal star. It is a runaway, unstoppable chain reaction. In less than a second, the entire white dwarf is engulfed in a thermonuclear firestorm. There is no core left behind, no neutron star. The entire stellar remnant is completely vaporized in an explosion of unimaginable ferocity. This specific type of detonation is a cosmic crucible for particular elements. The sheer, uniform violence of the blast is perfect for forging immense amounts of radioactive nickel and stable iron. In fact, a single type Ia supernova can produce a mass of iron greater than that of our entire Sun. This iron and nickel are then blasted into the galactic environment, becoming the raw material for future rocky planets. So the very ground we walk on, the core of our own world, owes its existence not just to the collapse of giants, but also to the stolen mass and thermonuclear annihilation of these once peaceful stellar embers. While supernovas forge elements in a frantic blizzard of neutrons, there exists a far more patient and gentle cosmic workshop. Deep within the tranquil hearts of aging red giant stars, another kind of alchemy is at work. This is the slow neutron capture process, or the S process, a method of creation that stands in quiet contrast to the violent chaos of a stellar explosion. Here, the environment is stable and the pace is almost leisurely. Neutrons are not flung at atomic nuclei in a frantic storm, but are instead added slowly and deliberately, one at a time. After a nucleus captures a single neutron, it often has time to settle to catch its breath. If the new configuration is unstable, it can undergo radioactive decay, transforming a neutron into a proton and effectively stepping one element higher on the periodic table before another neutron ever arrives. It is a meticulous, step-by-step assembly line, building heavier elements with the steady patience of a master craftsman. This gentle process is responsible for forging roughly half of all the elements in the universe that are heavier than iron. The strontium that gives fireworks their brilliant red color, the barium used in medical imaging, and even the lead that shields us from radiation, all of these were likely crafted in the calm, deep interiors of these aging stars. This is not a story of catastrophic death, but of a star's final, productive years, a long and steady exhalation that gradually enriches the cosmos. The star does not explode to release these treasures. Instead, over thousands of years, it gently puffs its outer layers into space through powerful stellar winds. The newly forged elements are carried away on these cosmic breezes, drifting out to mingle with the interstellar gas. This gradual contribution is a vital part of the galaxy's chemical evolution, a slow and constant drizzle of heavy elements that, combined with the violent downpour from supernovas, fills the galactic reservoir with the diversity of atoms needed for complex worlds and ultimately for life. This gentle farewell stands in beautiful contrast to the explosive demise of giant stars. For a star like our Sun, the end is not a supernova but a slow, majestic unwinding. After billions of years, it swells into a red giant, its outer layers becoming tenuous and cool. In these final stages, the star's core is a frantic factory, and powerful pulses ripple through its vast atmosphere. These pulsations act like a great cosmic breath, gently pushing the star's outer layers away. The star does not explode, it exhales. This expelled gas, now freed from the star's gravity, drifts outward, forming an immense and expanding cloud. At the center, the star's hot, exposed core is revealed. This core, now a white dwarf, is inconceivably dense, packing nearly the mass of our Sun into a sphere the size of Earth. Its surface is searingly hot, and it bathes the surrounding cloud of its own making in an intense flood of ultraviolet light. This radiation energizes the gas, causing it to glow with its own ethereal light. We call this glowing shroud a planetary nebula, a name that is a historical accident from a time when early telescopes made these objects look like fuzzy planets. In reality, they are among the most spectacular and intricate structures in the galaxy. The famous Ring Nebula, for instance, is not a simple sphere, but a complex, layered halo of glowing gas, a testament to the intricate final breaths of its central star. Within that glowing gas are the star's final gifts to the galaxy, elements like carbon and nitrogen, forged in the slow, steady alchemy of its last years. This is the star's legacy, not cast out in a single violent blast, but released in a long, gentle sigh that will eventually seed new generations of stars and planets. That dense, crystallizing ember is the ultimate fate for over 97% of all the stars in our galaxy. A white dwarf is a stellar fossil, the exposed core of a star that has gently shed its outer layers. Its composition is a direct chemical record of the star's entire life. For a star like our Sun, this final state is a sphere of crystallizing carbon and oxygen, squeezed by gravity to a density 1,000,000 times greater than anything on Earth. It no longer burns with the fire of fusion, but instead glows with the residual heat of its long and productive life, a thermal memory of its past brilliance. This is the quiet, dignified end for most stars, a slow cooling over trillions of years into a dark cosmic diamond. Yet within that silent, compact sphere lies the star's accumulated wealth, the carbon and oxygen it painstakingly forged during its main sequence and red giant phases. These are the very elements that, when scattered by stellar winds or a companion's theft, become the building blocks of life. The carbon that forms the backbone of every organic molecule in your body was once the central treasure of a star like our Sun, locked away in its white dwarf heart. This is the star's final, peaceful bequest to the universe, a legacy of fundamental elements held in trust, waiting for a chance to be released back into the great cosmic cycle. That leftover core, compressed beyond belief, becomes a new kind of cosmic object. If the collapsing heart of the star weighs between 1.4 and 3 times the mass of our Sun, it does not form a black hole. Instead, it is crushed into a neutron star. Picture an object with the mass of 500,000 Earths, yet compressed into a sphere no larger than a city. The density there is almost beyond comprehension. A single sugar cube of neutron star material would weigh more than every single person on our planet combined. This is not merely solid matter, it is a state of existence where atoms themselves have been obliterated. Electrons are forced into protons, fusing together into a seamless, swirling ocean of neutrons. The gravitational pull at its surface is so immense that if you were to drop a marshmallow from just 1 meter above, it would impact with the force of 1,000 hydrogen bombs. And its magnetic field can be a quadrillion times stronger than Earth's, a force capable of tearing apart molecules from thousands of kilometers away. The very birth of this ultra-dense remnant is an act of violent creation. The gravitational energy released during that split-second collapse is staggering, and it is this energy that helps power the supernova shockwave, blasting the star's outer layers into space. But the story of the neutron star does not end with its formation. It becomes a universe in itself, a seed for processes even more extreme than the supernova that gave it life. Some neutron stars announce their presence with a rhythmic beat that pulses across the galaxy. These are the pulsars, the universe's most precise lighthouses. Born in the supernova chaos that forges new elements, a pulsar is a rapidly spinning neutron star with an incredible trick. Its unimaginably powerful magnetic fields channel radiation into two narrow beams firing from its magnetic poles. If these poles are misaligned with its rotation axis, the star spins like a frantic cosmic beacon. As it rotates, these intense beams of radio waves, X-rays, or gamma rays sweep through the void. And if, by chance, one of those beams periodically flashes across Earth, our telescopes detect a perfectly regular pulse. The discovery of the first pulsar in 1967 was so startlingly regular that astronomers briefly nicknamed the signal LGM for little green men before the true, natural explanation was understood. This was the first direct proof that the theoretical neutron star was not just an idea but a reality. The clockwork precision of these pulses is almost unbelievable. Some pulsars spin hundreds of times per second, their rhythm more stable than the most accurate atomic clocks on Earth. This incredible regularity makes them powerful tools for astrophysicists. By tracking the subtle changes in the timing of these pulses, scientists can test Einstein's theory of general relativity with extreme precision, search for the faint ripples of gravitational waves stretching space itself, and even map the thin, invisible gas that drifts between the stars. Every pulse is a direct echo from the heart of a stellar corpse, a relentless reminder of the cataclysm that gave it birth. Yet even a pulsar's incredible power pales in comparison to its most volatile cousin. In the chaotic aftermath of a supernova, under the perfect and violent conditions of a star's collapse, a magnetar can be born. This is a neutron star that has been wound up to an unimaginable degree, possessing a magnetic field so strong it defies all earthly comparison. We measure its strength in numbers that are almost meaningless, quadrillions of times more powerful than the field that guides a simple compass needle. This is a force so immense it warps the very fabric of reality around the star. The magnetic field becomes a tangible presence, a crushing energy that can literally twist the shape of atoms themselves, stretching them into long, thin cylinders. The solid crust of the neutron star, a material far stronger than any steel, is not safe from this influence. This crust is under unimaginable strain, and as the magnetar's powerful magnetic field evolves and shifts, it can crack. These are not mere tremors, they are starquakes, seismic events on a cosmic scale. When a section of this ultra-dense crust fractures, it releases a cataclysm of pent-up energy. In a single, brief flash, a magnetar can unleash more energy than our sun will emit over 100,000 years. This energy erupts as a blinding storm of gamma rays and X-rays, a pulse of radiation that can travel across the galaxy. These titanic explosions do more than just light up the void. The intense flood of radiation and particles can trigger nuclear reactions in any gas and dust still lingering nearby from the original supernova. In this way, the magnetar continues the creative work of its birth, contributing to the nucleosynthesis of rare, heavy elements long after the main explosion has faded. For a brief period, these objects are the most powerful and terrifying magnets in the entire cosmos, a final, twisted monument to the star that died to create them. But the story of cosmic creation does not end with a single star's death. Sometimes it requires two stellar corpses locked in a final, fatal dance. When two neutron stars in a binary system spiral inward over millions of years, they radiate energy in the form of gravitational waves, those faint ripples in spacetime predicted by Einstein. This slow, cosmic pirouette steals their orbital energy, drawing them ever closer until they can no longer resist their mutual gravity. In the last few seconds, they plunge toward each other at a significant fraction of the speed of light, and finally they collide. This merger is not a gentle coming together. It is one of the most violent and energetic events since the Big Bang itself, a cataclysm known as a Kilanova. For a brief moment, this collision outshines every star in its host galaxy. The sheer force of the impact tears both neutron stars apart, flinging a small but incredibly dense fraction of their material into space. This ejected cloud is a superheated, neutron-rich broth, a perfect environment for the most extreme form of the Are process. The neutron density here is far greater than in even the most powerful supernova. Atomic nuclei are bombarded in a blizzard of neutrons so intense that they are forced to swell into the heaviest, most unstable forms imaginable, which then rapidly decay into stability. This is the cosmic factory where the majority of the universe's gold is forged. The platinum in jewelry, the neodymium in powerful magnets, and many other rare earth elements are also created in this frantic, neutron-saturated environment. For decades, astronomers theorized this was a primary source for these heavy elements, but the proof arrived spectacularly in August of 2017. For the first time, observatories detected both gravitational waves and a flash of light, a gamma-ray burst coming from the same event in a distant galaxy. The subsequent observations across the electromagnetic spectrum revealed the unmistakable signature of heavy elements being synthesized in real time, including vast quantities of gold. This single event was calculated to have produced an amount of gold with a mass many times that of our entire planet. This confirmed that these incredible collisions are not just theoretical curiosities. They are fundamental foundries responsible for seeding the galaxy with the precious metals we find on Earth. The wedding ring on a finger or the conductor in a smartphone are not just remnants of a dead star, but relics of a cosmic collision that briefly shook the fabric of the universe. This brilliant, fading glow is the Kilanova's final signature. It is the direct, observable proof of a cosmic foundry in action. When two neutron stars collide, they do not just vanish in a flash of gravitational waves, they leave behind a rapidly expanding cloud of hot, neutron-rich debris. This cloud is the Kilanova. For a few days, it can outshine its entire host galaxy, not with the raw power of the collision itself, but with a light born from the radioactive hearts of newly forged atoms. The energy source is the frantic radioactive decay of the unstable heavy elements created in the merger. Think of the ejected material as a cloud of exotic, superheated sand, where every single grain is an atomic nucleus that has been stuffed with an unsustainable number of neutrons. These overburdened nuclei are desperate to find stability. They achieve this by shedding energy and particles, a process we detect as a brilliant, multi-colored glow. The specific colors of this light are a dead giveaway. A blue tint early on suggests the presence of lighter heavy elements, but as the cloud expands and cools, a dramatic reddening takes over. This red light is the unmistakable fingerprint of the very heaviest elements, like gold and platinum, as they undergo their rapid decay. By carefully analyzing this evolving light show, astronomers can literally read the chemical composition of the cloud. They are watching the periodic table being written in real time. This is not theoretical physics, it is direct observation. Every shift in color, every change in brightness, tells the story of atoms being born from the ashes of a dead star's final, catastrophic embrace. That reddening glow of a Kilanova was a silent movie until we learned how to listen. The collision of these ultra-dense objects does more than create a flash of light. It actually shakes the very fabric of the cosmos. These vibrations are gravitational waves, ripples in spacetime itself that travel outward at the speed of light. For most of human history, our exploration of the universe relied entirely on light, from visible starlight to invisible radio waves and X-rays. We were essentially deaf to this other cosmic sense. That changed with the development of incredibly sensitive instruments like LIGO and Virgo. These are not traditional telescopes with lenses and mirrors. They are the most precise rulers ever built, using lasers to measure the distance between hanging mirrors over a span of 4 kilometers. A passing gravitational wave, a ripple from a distant cataclysm, will ever so slightly stretch and squeeze the space between those mirrors. The change in distance they are designed to detect is almost absurdly small, smaller than 1/10,000th the width of a proton. This is the experimental equivalent of measuring the distance to a star 4 light-years away with an accuracy less than the width of a human hair. It is an engineering marvel built to listen for the faintest whispers of the universe's most violent events. This new sense gave us ears to hear the death of stars. And in August of 2017, our new ears and our old eyes worked together for the first time in a watershed moment for science. The LIGO and Virgo detectors registered the distinctive chirp of gravitational waves produced by 2 neutron stars spiraling together. This signal alone was a monumental discovery, but what happened next defined a new era. Within seconds, space-based observatories detected a powerful burst of gamma rays coming from the same patch of sky. The gravitational wave signal had provided the cosmic address. Astronomers around the world immediately pointed every available telescope toward that point of light, witnessing the brilliant Kilanova unfold in real time. For the first time, we could both hear the crash and see the fire. This coordinated observation, known as multi-messenger astronomy, was like watching a silent film suddenly gain a soundtrack, color, and a narrator all at once. The data from both the gravitational waves and the light confirmed beyond any doubt that this spectacular collision was indeed the cosmic crucible where the universe forges its heaviest elements, including gold. We were no longer just theorizing about where these elements came from, we were watching them be born. Even the unbreakable bonds of a neutron star have their limits. When the collapsing heart of a supernova weighs more than 3 times our Sun, it crosses the final threshold. The inward crush of gravity becomes absolute, overwhelming every known force that could possibly resist it. Neutron degeneracy pressure, the very quantum rule that holds a neutron star together, simply shatters under the strain. The collapse does not stop, it accelerates, continuing into a state of infinite density. This is the birth of a black hole. At its center lies a singularity, a point where all the mass of the former stellar core is crushed into a volume of 0 size, and our current understanding of physics breaks down completely. Surrounding this unfathomable point is the event horizon, a boundary in space known as the point of no return. It is not a physical surface, but a mathematical line of destiny. Once anything, even a single photon of light, crosses this threshold, it can never come back. The black hole's gravity has effectively torn a hole in the fabric of spacetime itself. While the black hole is a cosmic endpoint, a place of pure consumption, its creation and the environment around it are not sterile. The violence of its formation and the chaotic systems that often surround it become powerful, if indirect, agents of cosmic change. The black hole itself may not forge new elements within its dark heart, but the journey toward that darkness and the maelstrom that can orbit it are crucibles of immense creative power. That silent, expanding remnant is not just a glowing cloud of gas. It is a natural particle accelerator of staggering power. The shockwaves rippling outward from the supernova blast create a chaotic frontier of intense magnetic fields. Within this turbulent zone, charged particles like protons and atomic nuclei become trapped. They are caught in a cosmic slingshot, bouncing back and forth across the shock front, gaining a little more speed with each crossing. This relentless process, called diffusive shock acceleration, can boost these particles to energies far beyond anything we can create in our most powerful particle colliders on Earth. Once they finally break free, they become cosmic rays, a ghostly rain of high-energy matter that permeates the galaxy. These are not rays of light, but atomic nuclei stripped of their electrons, hurtling through the void at almost the speed of light. They are the shrapnel from a stellar explosion, carrying with them a direct physical record of the violence that created them. Every second, thousands of these invisible particles pass straight through your body, a faint but constant whisper from the death of distant stars. But their journey is not always a solitary one. When a cosmic ray, a single proton traveling with the energy of a fast-pitched baseball, slams into a sedentary atom of interstellar gas, something remarkable happens. The impact is so violent it shatters the larger nucleus into pieces. This process, known as spallation, is a form of cosmic fragmentation. It takes relatively common atoms like carbon or oxygen drifting in space and breaks them apart into lighter, rarer elements. This is the primary source of lithium in our universe, the element that powers the batteries in your phone and laptop. It also creates most of the beryllium and boron found in nature. These are not elements forged in the hearts of stars, but rather shards created in the violent collisions that happen in the dark, empty spaces between them. So the supernova's legacy is twofold. It forges the heavy elements within its fire, and then its expanding shockwave acts as a cosmic shotgun, blasting the particles that will shatter other atoms to create the light ones we also depend on. But for the universe's true titans, even a normal supernova is not a grand enough finale. When a star is born with a mass dozens of times that of our Sun, its death is not a collapse but a direct implosion into a black hole. This catastrophic event unleashes a hypernova, a supernova on steroids, and often triggers the single most luminous electromagnetic event known to exist, a long-duration gamma-ray burst. The energy released in just a few seconds of a gamma-ray burst can exceed the total energy our Sun will emit over its entire 10 billion-year lifetime. This staggering power comes from a specific and violent mechanism. As the stellar core collapses past the point of a neutron star and into a black hole, the infalling material can form a swirling, superheated disk of matter, an accretion disk orbiting the newborn singularity. The physics at play here can launch two narrow, counterpointing jets of material away from the poles of the dying star. These are not gentle streams of gas. They are beams of plasma accelerated to over 99.9% of the speed of light, becoming what physicists call relativistic jets. These jets are like cosmic blowtorches, and they must drill their way out of the star. They rip through the overlying stellar layers in a matter of seconds, and when they finally break free into space, they release an intense, focused pulse of gamma-ray radiation. If one of these beams is pointed fortuitously in our direction, we can detect the burst from billions of light-years away. The sheer violence within these jets creates a crucible unlike any other. The environment is so extreme, with densities and temperatures far surpassing even a core collapse supernova, that it likely hosts a unique version of the rapid neutron capture process. This could be the primary cosmic source for some of the rarest stable elements in nature. Elements like tellurium and iodine, essential for biological function, and precious metals like platinum, may be forged in these relativistic blasts. So the very processes that create the most destructive beams in the universe also contribute to the elemental diversity that makes life possible, a paradox written in the death screams of the cosmos's largest stars. These three elements, lithium, beryllium, and boron, are the cosmic exceptions. They are not born in the furious heat of a star's heart or the chaotic blast of a supernova. Their origin story is one of destruction, not creation. It begins with a high-energy collision in the vast, dark emptiness between the stars. Think of the interstellar medium not as a true vacuum, but as a thin, drifting sea of isolated atoms, mostly hydrogen and helium. Traveling through this quiet sea are the cosmic rays, the atomic shrapnel from long-past stellar explosions. When a single cosmic ray proton, accelerated to nearly the speed of light by a supernova's shockwave, slams head-on into a sedentary atom, say a carbon nucleus drifting peacefully for eons, the result is catastrophic. The impact is so violent it shatters the larger, heavier nucleus into pieces. This fragmentation process is called spallation. It is a cosmic demolition, breaking down what stellar furnaces built up. From the fragments of that shattered carbon nucleus, the lighter, rarer elements emerge. A lithium atom here, a beryllium atom there, a boron atom there. They are the broken shards of a larger whole. This is why these three elements are so scarce in the universe compared to their neighbors on the periodic table. They are not forged in abundance, but created as accidental byproducts of violent collisions in the dark. The very cosmic rays that make this possible are themselves a legacy of stellar death, meaning that even this path of destruction is ultimately powered by the explosive end of a star. This subtle, continuous process of shattering and fragmentation is a vital, if quieter, pathway in the galaxy's grand chemical evolution, ensuring that the raw ingredients for everything from lithium-ion batteries to the boron in our cell walls are sprinkled into the mix of new solar systems. Deep within the most massive stars, a different kind of engine roars to life. It is a more complex and powerful way to burn hydrogen, one that requires a special ingredient to function. This is the carbon-nitrogen-oxygen cycle, a process that turns these three elements into a kind of cosmic clockwork. Here, carbon, nitrogen, and oxygen are not the final products, but the essential catalysts that keep the entire machine running. They act like a set of temporary tools being passed from one form to the next, all to achieve the same goal as in our Sun, fusing hydrogen into helium. But in this high-stakes game of atomic hot potato, the catalysts themselves are permanently altered by the process. The cycle has a bottleneck, a step where nitrogen-14 builds up because it is the slowest to react. This means that over the star's lifetime, it actively enriches its core with nitrogen while slowly converting carbon into oxygen. The specific balance of these three crucial elements is being rewritten from the inside out. While this cycle does not create a net gain of new heavy atoms, it fundamentally reshuffles the star's internal composition. This reshuffling is not a minor detail. It is a profound legacy. When the star finally dies and casts its enriched guts into space, the material it returns to the galaxy carries a distinct chemical signature, a higher abundance of nitrogen relative to carbon, a direct result of this catalytic process. This altered blend of elements then becomes part of the raw material for the next generation of stars and planets, influencing the very chemistry from which life could one day arise. This relentless fusion builds the universe's most common heavy elements. Deep inside a massive star, the core has already forged a wealth of helium nuclei. These are not just simple particles, they are the robust building blocks for everything to come. Each one is an alpha particle, a tightly bound cluster of 2 protons and 2 neutrons, essentially the heart of a helium atom. The star's immense heat and pressure now force these alpha particles to slam into larger and larger atomic nuclei. It is a step-by-step assembly line of cosmic construction. Start with a carbon nucleus, fuse an alpha particle onto it, and you get oxygen. Fuse another alpha particle onto that oxygen, and you get neon. The process continues, climbing the periodic table one alpha particle at a time. Magnesium, silicon, sulfur, argon, and calcium are all forged in this methodical way. These are the alpha elements, the fundamental bricks of rocky planets, and the essential minerals of life itself. The calcium that solidifies your bones and the oxygen that fills your lungs were once assembled inside a giant star through this precise, additive process. But the story these elements tell does not end with their creation. When that star finally explodes as a core collapse supernova, it scatters this entire inventory of alpha elements into the galactic environment. This enrichment leaves a permanent chemical signature on the galaxy. Astronomers can read this signature like a cosmic clock. They look at the atmosphere of an ancient star and measure the ratio of alpha elements, like oxygen and magnesium, to iron. A star with a high alpha to iron ratio is like a fossil from the early universe. It formed from gas that was enriched by the first generations of massive stars, which live fast, die young in supernova, and flood space with alpha elements. A star with a lower ratio, like our own Sun, was born later, after many smaller stars had time to live and die, contributing their own different mix of elements, including more iron. So by simply analyzing the light from a star, we can uncover the history of our galaxy's chemical evolution, tracing our own cosmic ancestry back to the violent deaths of the first stellar giants. The elements forged in a star's final moments do not drift through space as isolated atoms for long. In the cooling, expanding clouds of gas ejected from both supernova and planetary nebulae, something remarkable begins to happen. Atoms of oxygen, carbon, and silicon start to stick together, not in the chaotic frenzy of fusion, but in the calm that follows the storm. They coalesce into microscopic solid particles, the cosmic dust that will become the building blocks of future worlds. These are not mere specks of dirt. Each grain is a tiny, crystalline record of the star's internal alchemy, a frozen snapshot of the specific nucleosynthesis that occurred in its heart. A grain born from a supernova might be rich in silicon and oxygen, forming a minuscule seed of silicate rock. A particle condensing from the carbon-rich wind of a red giant, however, could be a tiny diamond or a flake of graphite. This stardust is the universe's primary raw material for planet building, but its role is far more active than simple construction. These countless microscopic grains form a protective fog within the vast clouds of interstellar gas. They act as shields, absorbing the harsh ultraviolet radiation from nearby stars that would otherwise break apart delicate molecules. On the sheltered surfaces of these dust grains, single hydrogen atoms can safely meet and bond, forming molecular hydrogen, the cold, stable fuel required for new stars to ignite. Without this dust, the galaxy would be a much brighter, hotter, and ultimately sterile place, incapable of forming the cold, dense clouds where star birth begins. So the iron in your blood and the calcium in your bones were first delivered to our infant solar system encased within these specks of stardust, the final, essential gift from a generation of long-dead stars. This gradual enrichment writes a chemical history across the cosmos. The very first stars, known as Population 3 stars, were titans made of almost pure hydrogen and helium, the only elements the young universe possessed. Their lives were brilliant and brief, ending in spectacular supernova that, for the very first time, polluted the pristine cosmic gas with newly forged heavier elements. When the next generation of stars, called Population 2, condensed from this now enriched material, they already carried a tiny but crucial trace of metals within them. This cycle repeated over and over, with each stellar death contributing its unique chemical signature to the galactic reservoir. The gas clouds that collapsed to form our own Sun, a relatively young Population 1 star, had been seeded and reseeded by countless stellar ancestors. This is why our Sun, and by extension our entire solar system, is so rich in elements like oxygen, carbon, and iron. We are not made from the raw material of the Big Bang, but from the well-processed remains of a long lineage of dead stars. The term astronomers use for this is metallicity, a simple word for a profound concept, the proportion of elements heavier than helium found in a star or a cloud of gas. It is the universe's primary metric for cosmic maturity. The oldest, most primordial stars in the halo of our galaxy have an extremely low metallicity, a chemical fossil of an earlier, simpler time. Our own Sun, by contrast, has a relatively high metallicity, a clear sign that it is a child of a well-enriched modern galaxy. This means the specific blend of elements that formed our planet, from the iron in its core to the silicon in its rocks, was only possible because of the specific types of stars that lived and died in our galactic neighborhood before the Sun was even a glimmer in a nebula. We are the direct product of our galaxy's long and violent chemical evolution. Our entire solar system is a monument to this ancient cycle of stellar death and rebirth. Roughly 4.6 billion years ago, a vast cold cloud of interstellar gas and dust began to collapse under its own gravity. This was no ordinary cloud. It was a rich chemical soup already seeded with oxygen, carbon, iron, and silicon from countless stellar explosions that had occurred over billions of years. This material was the legacy of those long-vanished stars, a cosmic inheritance that would become the very substance of our Sun and its planets. The proof of this dramatic origin is not just a theoretical model, it is something we can hold in our hands. Ancient meteorites that fall to Earth contain microscopic grains of material that are actually older than the Sun itself. These are literal stardust, tiny diamonds, and silicon carbide crystals that condensed in the cooling atmospheres of red giant stars or in the expanding debris of supernova. They were drifting in that primordial cloud, were incorporated into the earliest solid bodies of the solar system, and have survived unchanged for over 4.5 billion years. They are time capsules carrying the direct physical signature of their stellar parents. This means that every single element on Earth, with the exception of the primordial hydrogen and a little helium left over from the Big Bang, was forged in a star. The silicon in the rocks beneath you, the oxygen you are breathing right now, the carbon that forms the backbone of your DNA, all of it was once part of a distant, dying sun. Your very existence is a direct and physical link to the most violent and creative events in the cosmos. These sudden celestial visitors were meticulously recorded by watchful astronomers long before the invention of the telescope. Across cultures and continents, scribes in China, Korea, and the Islamic world, along with possibly Native American artists, noted the appearance of a brilliant new star in the constellation of Taurus in the summer of 1054. It was so bright it was visible in broad daylight for 23 days, and it lingered in the night sky for nearly 2 years before fading from view. This was not a star being born, but a star meeting its violent end. That historical guest star is the very same supernova whose beautiful remnant we now call the Crab Nebula, a tangled web of glowing gas still expanding outwards today. These ancient records are far more than just historical curiosities. They are vital data points providing a timestamp for one of the universe's most energetic events. By knowing exactly when the light from that explosion reached Earth, modern astronomers can measure the expansion speed of the nebula we see now and work backwards to understand the precise mechanics of the blast that created it. This creates a profound bridge between human history and cosmic violence. The same event that was dutifully recorded by a court astronomer in ancient China is the very same cataclysm we study with space telescopes today. its remnants still actively forging new elements and pumping energy into the interstellar medium. Each of these historical supernova, like the one observed by Tycho Brahe in 1572 and Johannes Kepler in 1604, offers another snapshot, another chance to calibrate our understanding of stellar life cycles. They tell us that such galactic explosions are not rare, abstract events, but recurring chapters in our galaxy's story, with our own solar system existing in the aftermath of such ancient violence. What other stellar explosions from centuries past are still expanding silently in the dark, waiting for our technology to finally find them? These historical records are now amplified by a cosmic surveillance system of incredible power. Our planet is now orbited by a fleet of robotic observatories, each designed to see the universe in a different light. The Hubble Space Telescope captures the intricate beauty of supernova remnants in visible light, revealing their delicate filaments and violent structure. The Chandra X-ray Observatory sees the multimillion-degree gas heated by the shock waves of these explosions, mapping the energy that forges new elements. And the James Webb Space Telescope peers through dust with its infrared eyes, studying the very formation of those dust grains in the cooling ejecta of dying stars. Together, they act as a forensic team, each instrument examining a different piece of evidence from the scene of a stellar crime. The data they collect is not just a pretty picture, it is a quantitative test of our most fundamental theories. When we observe the specific wavelengths of light, the spectra, from a supernova remnant, we are reading its chemical composition like a barcode. We can see the direct signatures of oxygen, silicon, and iron that our models predicted would be there. When we analyze the light from a kilanova, we can track the reddening glow that confirms the creation of gold and other heavy elements in real time. Every observation is a check on our understanding of nucleosynthesis, confirming that the violent processes we theorize are not just elegant ideas, but the actual engines that built our material world. This constant dialogue between prediction and observation, between model and reality, is how we move from wondering about the stars to truly understanding our profound connection to their spectacular deaths. This gradual quieting is the universe's inevitable destiny. For billions of years, the cycle of star birth and death has been a furious engine of creation, but every engine requires fuel. The primary fuel for this cosmic factory is the vast reservoir of pristine hydrogen and helium gas drifting between the stars. With each new generation of stars, this raw material is consumed. Massive stars burn through their fuel in a few million years and then explode, scattering their newly forged elements back into space. But a significant portion of that original hydrogen and helium gets locked away forever inside the long-lived corpses of stars, the white dwarfs and neutron stars that will slowly cool over eons, and the black holes that simply swallow matter whole. This means the total amount of available gas for making new stars is constantly, irreversibly decreasing. The rate of star formation across the cosmos peaked billions of years ago and has been in a steady decline ever since. We live in a universe that is, in a very real sense, running out of the primary ingredient needed for its most spectacular acts of creation. What does this cosmic fuel shortage mean for the future of element production? The brilliant stellar explosions that forge the elements are directly tied to the birth rate of massive stars. Fewer new stars means fewer supernova. Fewer supernova means less oxygen, silicon, and iron being blasted into the void. The rare and violent collisions of neutron stars, which create the universe's gold and platinum, will also become increasingly infrequent events as the stellar population ages and binary systems merge or drift apart. The universe is slowly shifting from a state of furious, active creation to one of relative quiet. Future galaxies will be richer in heavy elements, having been chemically enriched by all the stellar generations that came before, but they will be far poorer in the brilliant, cataclysmic events that created those very elements. The cosmic cycle of matter is gradually winding down. The great forges of the cosmos are cooling, their fires dimming as the available fuel is spent. This leads to a profound and sobering thought. We exist during a remarkably vibrant chapter in the universe's story, a golden age of stellar life and death that manufactures the diversity of atoms necessary for planets and life. In the distant future, the raw materials for new worlds and potential life will still exist, but the mechanisms to create and distribute them will have slowed to a near standstill. The universe will become a quieter, darker, and more settled place, its legacy of elements a testament to the brilliant, violent past that we are fortunate enough to witness today. From the quiet fusion in a star's core to the spectacular violence of its death, we have traced the journey of element creation. The iron in your blood, the oxygen filling your lungs, and the calcium strengthening your bones are not mere accidents of chemistry. They are the direct inheritance of cosmic violence, the scattered remains of stellar giants that lived and died long before our sun was born. The gold in a wedding ring and the uranium that can power a city were forged in frantic neutron blizzards, while the silicon in the ground beneath your feet was assembled layer by layer in a star's final, desperate years. Every atom of your being carries this incredible history. We are, in the most literal sense possible, made of stardust. This is not a poetic metaphor, but a scientific fact written in the very elements that constitute life. It is the ultimate testament to a universe that is not static, but dynamically creative, where endings are perpetually recycled into beginnings. The death of a star is not a final silence, but a transformation that seeds the void with the potential for new worlds, new stars, and even new life. This knowledge forever changes our perspective. The next time you look up at the night sky, see it not as a distant, cold emptiness, but as a grand, connected tapestry. You are looking at the very factories that built you, the ancient graveyards that became your cradle. We are the universe become conscious, looking back on itself. What part of this cosmic story resonates most deeply with you? Share your thoughts and reflections in the comments below.